you may recall last time that we were doing, let's see, we were doing as x, oh, sorry. We were doing this in what was called the Schrodinger picture, which is when you would take a state and we use the Sx plus state. We let it time evolve. Again, U is a unitary operator, but it's pretty much universally used for the time evolution operator for over a macroscopic amount of time. Okay, and of course this is alpha. So we allowed the state to evolve in time. And again, I see this very intuitively, and this is called the Schrodinger picture or Schrodinger frame or Schrodinger representation of time evolution, and that's versus Heisenberg. And what that, of course, is, as I alluded to several times, and I'll get a little ahead, which is that we're going to allow the state to stay static, and we're going to come up with a mathematical representation of the operator changing over time. So you may recall, sorry, my handwriting is bad today, that we did spin procession. And so when I actually did this in the Schrodinger frame, what did we get? We got, so this was, now remember, of course, it depended on the, you have to have knowledge of the initial state. You can't say that this is true in general. That's absolute nonsense. So we started with it, so I'm just reminding you what we did last time. Oh, we did that. I'm just reminding you what we did last time. And I know that we're the S plus frame because cosine at time 0 is 1. So clearly, so if the spin in the z x direction is h bar over 2, I'm clearly in the Sx. I mean, let me write that down, right, so you don't get lost. That's right. I keep wanting to write a T. So there you go. So anyway, just to make sure you're not going to look at your notes and kind of forget what happened. And anyway, I'm not going to remind you what we did to do this. It was rather involved. And, you know. Okay, so we're going to do the same problem again. So we're going to do the same problem again. But what we're going to do is we're going to figure out how the operators change in time, and we're going to let the states stay by themselves. Now, the reason I think it's done is because it can be obnoxiously difficult to figure out what, like, the hydrogen atom states are, S and P and all that. Then to try to make them evolve in time, and remember there's rules for that, okay, the hydrogen 1s won't evolve in time, but of course, you know, a little bit of S, a little bit of P state, which is actually what you're dealing with all the time, that will evolve in time. That sounds like it could be very difficult to deal with. So you've gone through all the work to figure out what the states are. Maybe if you let those lie alone and you can figure out what your time-dependent operators are, it might actually be kind of an easier way to do this. Now, the second thing I can tell you is that based on today's lecture, regardless of whether it's sensible or not, this is how you're going to see papers and talks. So after the end of the day, if you go to any PChem paper or talk and they talk about time-dependent quantum, which many of them do, you should be able to follow it. So that's kind of one of our bigger goals here. Okay, so how does this work? Okay, now first, note that we're going to use, again, we're going to use a notation from the book because it actually ends up being really important. And so what that is that, so if the Heisenberg view is time dependent, then the operators as you've known them, think of every operator that we've done. X is X, P is H bar over I, single derivative. Spin is, okay, a matrix. Anyway, follow them. Those are the time evolving operators just at time 0. So what you expect is that there's going to be perhaps the same operator, but there's going to be like a t in it somewhere. In fact, often it turns out that the way this is going to look is it's going to be the operator as the time evolving operator will be the operator as you've known it plus a function of t. And that way when t is 0, that term is the variable. So you see what I mean? It's going to be like in addition to the operator we've already known, and that way at time 0, you will actually be working with the operator that you've always known. All the ones that we've done, which is a fair number. Okay, so anyway, just heads up, that's not always going to happen, but it generally is what I find happens. Okay. All right, next thing is, oh God, this is something. Okay, so if you could, just make sure you put down what pH means. Okay, so here, let's let this evolve in time. And notice I'm putting some space. So put some space here. Of course, the transpose of the time evolution operator has T in it. The Schrodinger frame, we've never had an operator with the letter T in it, up until the time evolution operator, but that's right there. And then, of course, now, we've done lots of matrix. In fact, you even, on your exam, you even saw what that looks like for the SC plus state, right? It was a guy on the exam, the last question, for SC plus state, if your Hamiltonian is a magnet in the z direction, these are just a diagonal, either the minus energy, plus energy, even the minus energy. Anyway, you've seen this. So what's the problem? The problem is that you figured out what these were for a particular state, right? To figure out what this was, to put this in matrix form, you had to apply, plus minus plus minus. Okay, but you can't do that here. I'm trying to figure out the operator. Once I have the operator, then I figure out its matrix representation. I can't work backward. If I say I know what these operators are, like you did on your test, that means you've already applied a state. You've already decided the basis set and all that jazz. We're not doing that. We're just trying to figure out the operator to begin with. So you can't follow that approach. Okay, so here's what happens. So it turns out that what we're going to do is we're going to take the derivative. We're going to take the derivative of all this. So that's why I said leave a space. If you didn't listen to me, that's your fault. Okay. Now again, the Schrodinger operator doesn't have anything in it, so we're going to have a product rule, and kind of like how we had with that identity. So that identity, and by the way, that identity, so that one more question you had, remember that? E to the B, A, E to the B, lambda B. Right, so we're actually doing this. That's what we were doing. That's an identity for time revolution in the Heisenberg picture. So anyway, so that's one of the ways to solve this. I actually won't focus on that too much, but I see that in the literature, that identity that you were proving on that homework. I see it in there. Okay, anyway, so I'm doing product rule, so I'm gonna do the derivative of that, and then I'm gonna leave it alone. Again, this thing never gets touched. And now I'm going to do the derivative of the other operator on the other side because it has time in it. Because I have two functions of time. Okay, now. Now I always hate this, but now I'm doing a derivation, but I have to stop and I have to do another derivation. So, I hate it when that happens. comes up frequently in quantum. Okay, so I'm stuck here. And what my approach is I'm going to try to do something about this because now I've got derivatives. What I really want to do here is as I'm going to do, by the way, is I'm going to make a differential equation, right? So I've got the function changing, and if I can get it equal to a function, even if it's of itself, then it's just a standard Diffie cube. And God knows we have all kinds of textbooks, even from the 18th century, on Diffie cubes. So I need to get rid of that, though, if I'm going to have a standard Diffie cube equation. Okay, here's how we do that. Okay, if you want to do simple time evolution, so of course you want to just move something along a very short amount of time, and let's move an operator. So this is where it's a little funky. We're actually doing this with an operator. Then this ends up being, of course, so we're assuming that we can operate on operators. I don't know if there's a proof for that, but anyway, that's the idea. So I'm a little bothered at this. I think the book just spits this out. And while this certainly looks like a translation operator, we just assumed that changing P for H made it the time evolution operator based on the analogy to Poisson brackets, the classical analogy. We did that to states, the time evolved the states a short amount of time, and now we're doing it to operators. And the book just says you can do it that way without really proving it. Okay, now I'm going to do some algebra. And what I'm doing is I'm creating a differential. Okay, so I have this over here. What I've done is I've brought it over there. And, okay, so what is that? That is, sorry, it's painful to follow my own notes. Over I. So I bring it over. Okay, so what did I do? Okay, so this is actually still negative, so I'm going to drop the I below. Okay, you see how I did that? So you know what, let me, I think I follow it, but I want to make sure you follow it. I just realized that I had reversed the order of things. That kind of sucks. Okay, so this is still here. What I have is this is over here, but I bring it over here. Okay, now I'm left with minus I. Okay, now what I can do is I can, I'm just going to eat the minus sign by bringing I at the bottom. And now what I've got is the operator changing a very minuscule amount of time divided by a minuscule amount of time, which of course is the definition of a derivative. Which is the derivative of the operator in the Heisenberg picture with respect to time. Okay. So what does that do? Okay. And also let me point out, you can do this with let me make sure that it's together. Sorry, where is that correct? No. What if I? No. Sorry, what is wrong with me? I'm just kind of a little bit lost. problem. It's right here. Okay, now why am I doing that? Let's see, because that puts me, what that does is allows me to put something here, right? So you see what I've done? Is again, remember I was saying the goal here is to have this in a Diffie cube, but these are weird. Right? I have to have DDT on one side, and you can't have any more DDTs on the other side. If not, it's not a Diffie cube, right? You're gonna have DDTs on one side equal to some stuff on the other side. So I've got these DDTs here. Now I just figured out how to get rid of it, right? So this one, so using the time evolution operator over a short period of time, I'm able to get rid of this. And likewise, if you do the same deal, I also have to get rid of this, right? Okay, and now if you do the same thing, what you're going to get is, this is going to look a little different. And the reason is because, notice that, make sure I get this right. I have two H's here, don't I? God. Why did I do that? What's wrong with me? Sorry, this is really hard, by the way. Okay, notice you got HU and then here UH. So, just look out for that. Okay, sorry about that. This I have to admit, this really is pretty painful. Okay, all right, now I was doing a derivation. This is just a product rule. And now I have some identities that will allow me to get rid of the derivatives on the right side, and then I can leave the derivative on the left side, and now I've got a Diffie cube. So that's where there's a big advancement. Okay, so I'm just writing this down. Here, I'll make sure that I don't I gotta get rid of the plus t's. It's not necessary at this point. Just nothing magically happened with him. And then I've got here. Let me put that up front. So now I'm putting in this substitution. Okay. And okay, now you guys in the back, you can see this, because there's another trick, and then I'm going to have to wipe out the board and start over here. Again, this is nuts. Okay, so what's really nutty is here and here, I'm going to kind of resolve an identity. I'm basically going to resolve an identity. What I'm going to do is I'm going to do this. Here. Okay, so I'm inserting, since time is unitary, which is, so, it's equal to 1. Time evolution times its transpose is the number 1, so I'm inserting it in between there. Now, this step is actually kind of logical if you kind of just put it in your mind, but here, let me write it out. What I'm doing is, I've got, what I'm doing here is now you can see that I'm time evolving. Here, let me just write the whole damn thing out, it'll be very clear. This is actually the one part that's the most clear. Again, so just don't forget, I'm just doing some algebra. I started with a product rule. That was about as hard as it got. Then there was a little bit of a funky proof. It was a little odd. There's two of them. And you may notice that I'm getting close to a commutator. Actually, I'm at a commutator. So the trick here, again, was getting rid of derivatives on the right side so that you had a Diffie cube. And because of the minus sign on the left term, I've actually just created a commutator. Okay. So let's see here. I am evolving. So remember, this is the Schrodinger one. But notice what I've done here is I'm time evolving the Heisenberg time-dependent operator. And what have I got here? I have that there, but what happens when you put it in between two time-evolving unitary operators? Well, what is this? What? Remember, I'm deaf. We started out, in fact, I'm looking at it. This is the Heisenberg representation, which is this. They're the same function. You see, now I've got a Diffie-Q, right? So there's the time-evolving Hamiltonian. There's the Heisenberg version of the Hamiltonian. Here's the Heisenberg version of the operator that we're actually interested in. And we have the same thing going on here. Okay, so now the time evolution, again, so one thing is be really careful what is the Schrodinger non-time evolving whatever, and which is the Heisenberg time evolving whatever, this being the whatever. Okay. So it is the, notice I apparently have reversed them, but that's because the minus sign unfortunately came up front, so you have to flip these, and that's why this is actually on the right side. And remember that this actually does mean something. This, that, minus that, this. So there is an order to this, so don't forget that. If you get that wrong, you picked up a minus sign. Okay, so what we've got here is we've got a Diffie-Q. So what's funky about this, I mean, it's cool that we've kind of managed to take this hideousness and simplify it. And another thing is that commutators, one reason to do this is not because it's way easier to write, but we've been dealing with a lot of commutators, right? So you can bet that this operator H minus H operator might just be like, oh, it's just SX, right? It might simplify to something very simple. Oh, it might simplify to 0, which would really be great, right? Because ddt of 0 is very easy to solve. The next thing to notice that's funky though is that instead of a function where Diffie-Qs, you solve functions. The Schrodinger equation is a Diffie-Q. It's a second order differential equation. The solution is the wave function. Here, I'm glad we have a first order Diffie-Q. Those are way the hell easier to solve. What I find strange is that we're not solving for a function, we're solving for an operator. Now, operators are often functions. Take the position operator. It's just the letter x. That's a function. But the momentum operator is a derivative. And I've never solved a derivative in a Diffie-Q because what the hell? Yet here we are. So this is kind of a neat thing. A new and neat thing. Okay. Next thing. We've got several more steps to go. So what about H and E to the minus IH? Okay, what about that? What can you think of? Name a single property that might be hideously important about an operator and a function of that operator. What? I can't hear. Remember, I'm deaf.
Commutators.
They're commutators, right? Well, I mean, you can commutate. You can figure out the commuter of anything. It's just, is it 0 or not? So in this case, what's the commutator of the operator and its function?
0.
It's 0, right? So you use the term correctly. So they commute. When you say they commute, it means you mean that they're 0. Now what that means is that you can do stuff like, well, okay, so let me write that down. And so of course that's U. So the same for the transpose, obviously. Therefore, everyone gets that. Yeah, what's this?
Just
Just an H. Right, just like we use the fact that U transpose is the number 1, no matter which order you put them in, we're doing that here. So notice that in the big picture, we inserted these, and again, we can insert them because they're 1, but what it did was, it basically actually allowed us to knock one out. We're able to knock out, if we inserted this one, but we're going to knock out that one, and here we inserted this one that ultimately allows us to knock out that one. So in a weird way, we simplified it. Okay, so now you know that what I can do is I can redo the derivation, and oh heck, why don't I? Let me just start here. I hate to write all this down again, but why not? Okay, minus 1 over I h bar, and again, okay, so I just wiped this out. That's all I did. I don't actually do this in my notes because it's kind of obvious. I hope it's obvious at this point. Okay. So there you go. And now you have really clear. Writing the same thing down again. 1 over I h bar. Now I'm going to write the commutator. Same function. And just the regular. Okay. Oh, God. Yep. This is called. It's a great name. Heisenberg equation of motion. God, I want to go ahead and cancel class already. How much? Oh God. We'll mostly finish up, but I feel like we've done a whole class worth of stuff. Anyway, hopefully not too hard, right? It was kind of a whole bunch of algebra more than anything. Some tricks with commutators. Those of you who have already met for the test talk, I mentioned commutators are so much more important than you realize, even though we've been talking about them quite a bit. You can never say enough about commutation because it turned whatever the hell this was, which is ridiculous, into something that ends up being kind of simple looking. Okay, now let me just tell you where we're going with this. This is not simple. I told you, this is the hardest part. Number 2, the reason it's hard, by the way, the thing you've got to be careful about. This is not the operator as we've known it. This is the time evolving operator. Derivative of the time evolving operator is equal to the commutator of the time evolving operator. What the heck, I'm still disturbed that this is solvable, right? This is an equation with the same thing on left and right. You're supposed to solve for it. That shouldn't be possible. Y is equal to a bunch of x's, not y is equal to y. What the hell do you do with that, right? But that's what Diffie cubes are. So we can solve it. Of course there's a trick. But this is not the operator as you've known it, right? So that's where it gets difficult. Okay, next bit, and this is more of a practical difficulty. Every operator is solved differently. Gotta love that. Now remember I told you one thing I don't like about the traditional physical chemistry way of teaching quantum is that you just learn example problem after example problem. And I don't like that because every problem is solved differently. It's very unsatisfying, but every problem requires a completely different mathematical approach. Guess what? Every problem requires a completely different mathematical approach. No two operators, no Heisenberg representation, no time-evolving operator is solved the same as any other time-evolving operator. Oh my God. So let's do a whole bunch of them. Check out what's on the second page of your sheet. All right, there's position. Momentum is easy. There's position. Hey, we're not doing that. We're actually going to do spin procession again. Then we'll do that one. I'm just saying. Every one of them is different. So heads up on that. Okay. With that said, that probably unappealing statement on my part. Spin procession again. Let's solve what we already solved, which I think is on the first page. Anyway, you got first page, second page. You can see I'm giving you examples on how to solve time-evolving operators because, again, it really gets so detailed. More think this was bad as nothing. So let's go ahead and do spin procession, and I may have time for position. And another thing is it depends on the Hamiltonian, right? That's not only is, of course, everything different depending on what your Hamiltonian, what your operator is. Again, the mathematical approach to solve the problem will also be different, regardless of the commonality of this. Okay, let's do this again. Let's redo it. All right. Now, the one good thing is, now remember, we're assuming that the Hamiltonian is not changing explicitly with time. So we're putting an electron in a magnetic field, and we've talked about it's going to be in the z direction, because why the heck not? Remember that there's a bit of a math trick to solve this, where you have an upper and a lower quantized energy level, and the angular frequency between those two states, which is what you measure in absorption, would be the angular frequency. So there's a little bit of a math trick to show that you can simplify. Remember, it's not a derivation, it's just a manipulation of units. It's way the hell easier to deal with it this way. I hate writing all that crap down over and over and over and over and over again. Okay, so there's that. Okay. Now again, I am going to be just writing. It will be difficult not to get lost, so try your best. So again, so I'm writing the Heisenberg. I'll put a T in there just to emphasize that. I may forget to do that sometimes. I'm putting a little H and I'm putting a time dependence to just dramatically emphasize as much as possible what's what. Now again, because you see the unitary and the operator, remember the operator has a minus, and so the transpose happens to be plus. So that's of course the Schrodinger picture. The Schrodinger is the same as the Heisenberg at time 0, so I'll just leave that off. Sx is what you've known, so h bar over 2 plus minus h bar over 2 minus plus. We'll put it in matrix form. Again, you know all that. Then hopefully burned into your head. Okay, so there's that. All right, now let's do this. Let's write down the Heisenberg equation of motion. The derivative of this function is, and again, I will try to point to commonalities. And sometimes, as much as these are different, I do notice sometimes there are some things that are similar-ish. So this is one type of derivation of a Heisenberg time-evolving operator that I've seen reflected, that the approach is somewhat similar to a couple of others. So this is representative-ish of a couple of things. And what I'm doing is I am going to use the fact that the Hamiltonian, where the hell is it? Oh. What's gonna happen here is that the Hamiltonian is basically another operator that I already know quite well. So it doesn't bother me that I marked that up. Okay, so again, the approach in this case, which is common to a handful of others, is that the Hamiltonian is actually another operator, and I know a lot about that operator. So that's what's going to be happening here. Okay, so again, I am writing the definition of the Heisenberg time revolving operator. Transposed unitary, not time revolving. Okay, because this is a commutator, I'm now reversing that. Transposed because it's positive. Again, this is not time evolving. Minus because that's the operator, not the transpose. Transpose positive, operator is negative. Okay. Okay. All right. Right, now I gotta remind myself what the heck is happening. Okay, so what do I do here? Math is that okay, let's see here. All right, here's the trick. Here we go. Again, it's a trick. This trick I'm using is how I solve this one. What can I do with these operators? This operator is this function of that same operator. Name anything I can do with this. Given that this is an operator and this is a function of that operator, which has been brought up many, many times today and on the exam.
They commute with you.
Switch them. Well, if they commute, then switch them. Switch them. You're like, where the hell is this going? I don't actually know. Because I've forgotten at this point myself. Okay, now I remember. More. Okay. Now we will get through this one. The other example, we're going to do one other example, but we'll just do that one tomorrow. Okay, just make sure you know that this is the time 0 one. Okay, so I'm just switching those. Okay, so the reason I've done that, again, this is a way to do a couple of these, is note that I've got this thing on the left of each term, I've got this on the right of each term, and I've got SH, HS. So the trick here is to do some algebra with a commutator. Here's how you do it. And it turns out, again, this is just an algebra problem. I know it's not super obvious, but again, it is actually way more straightforward. What you can do is factor it out. And now I'm going to just put the commutator here. Okay. There you go. There you go. This is just algebra. So if you write this sucker out, if you write this sucker out, you'll see that this and that are the same thing. This is here, it's here, this is there, This is there. Okay, so it's all, everything's actually taken into account. Okay, now what? Okay, so now let's look at this. Check this out. Okay, this is actually right, because the Hamiltonian is just, remember this is like 5 joules or whatever, sorry, 5 per seconds. So it's a number, it can get factored out. So now I've got Sx and Sc. What's that? Minus Sy, but there's an IH in there too. I'm actually, so that's minus IH bar. Right, but no, yeah, minus, but don't get the IH bar. And you can see why, because it's actually kind of awesome, because it's actually going to kill that, that one right there. Remember, again, these are not time evolving. So that's, as I mentioned to you, of all the pain that has been today, don't forget, don't lose track of when you're dealing with a non-time evolving versus a time evolving. If you lose track, you're dead, right, for obvious reasons. So anyway, so again, I've actually got a little bit of an aside. Got a little bit of an aside here. Okay, so let's continue. Okay. Let me go back to the big picture. Notice how I put all this H and T, right, to make sure you didn't get lost. So that's how you know. Okay, so minus IH bar over IH bar. Okay, the IH bars are gone. That looks bad. That's better. That's pretty. Yeah, these things didn't go away. Let me write all that down again. And we are actually almost done. It doesn't look like we're done, but we actually almost are. So, I hope you can see all that. I can't remember what I put in that handout. I wasn't looking at it, I wrote it. I was looking at it before the class, I printed it out, but, okay. So there you go. Time derivative of the x operator is equal to Sy. All right, now I need to know what Sy is of time t. So now everything we've done today has to be repeated. I told you this sucked. Okay, guess what? Now we're having Sy. So let's just say we did that. Is guess what? Okay. The time derivative of Sx is equal to time evolving Sy. The time evolving of Sy is equal to Sx. Uh-oh. What do we do? It's hopeless, right? There's no way to solve that. The derivative of one function is equal to another, which itself is equal to the derivative of that first function. What would you do? Ever seen anything like that before? With the big hint being you've seen it many, many times, even your last homework. Recall that you did this problem on your last homework, just with different letters? Huh? Half of you are saying yes, because you're the ones who did it? right? Sorry to push your buttons. Yes, yes, you have seen this before. It's coupled differential equations, which is on your handout. Okay, so real quick, I have just enough time to begin this. And again, it's on your homework. Okay, I am solving. Notice that what I've done. I'm not going to put little h's. So I just solved for sy. So what I'm now going to do is, so remember this trick. You take the derivative of something so that you get the double derivative of something else. And the reason you do that is because then okay. So what I've done is I've basically taken this, I've done the double derivative. Because, so I've got the double derivative of sx now equal to the derivative of sy, which is actually equal to sx. So you see what I've done is I've managed to bring this into a diffie, a double, so it's a double differential, right? So, yeah, I'm just gonna, going to do that. And that looks like that's the world first plus. There we go. Okay, now you've seen this before? Double derivative plus function is equal to 0. Right, so it ends up being, here, I'll stop here and just finish up next time. Let me point out what will happen. Now again, do this with Simple Lab or whatnot. But just like we solved a free wave with e to the ikx or e to the minus ikx, we actually, like the second day or third day of class, I showed you how to solve a double derivative. I showed you how to solve this equation. And it is e to the ikx, a free wave, or e to the minus ikx. So we run into the same thing. Now, the way it then works is that you use boundary conditions. And therefore you're going to figure out that A is blah and B is blah. These are actually going to be operators. Notice that the operator over time, where's your SX? Where's the operators on the right side? There's an operator on the left, but there's no operator on the right. That doesn't make sense. Okay, it turns out that initial conditions make the A and B. Those are where the Schrodinger operators, the operators that we've been doing, that's where they're hiding. So we'll finish that up next time. It's on your handout so you can see it. But there you go. We'll finish that up next time. Oh God, I'm late. I gotta run